Hello there. In this video we're going to investigate a very particular type of relation known as a linear relation. So the following theorem states, let xy be a collection of points such that ax plus by is equal to c, where a, b, and c are arbitrary real numbers. Then the graphs of all of these particular types of relations construct all of the possible lines. We're not going to prove this theorem here, but we're just going to take it as an assumption and investigate some of the particular properties of this relation. Alright, so let's take, for example, ax plus by is equal to c, and we're going to see if we can find some special cases that we actually already are aware of. So let's consider the special case that a is equal to 0. So when a is equal to 0, we get the equation by is equal to c. So notice that this equation only has y. So if this equation only has y, then this equation represents what type of line? So if you remember, this is the equation of a horizontal line. Let's consider another special case. Let's consider the case where b is equal to 0. So that's the case we get the equation ax is equal to c. So this equation only has x. So what type of line only has x in it? So this is going to correspond to a vertical line. So let's consider the case where both a and b are equal to 0. If that's the case, we get the equation 0 is equal to c. So this has neither x nor y. So if that's the case, then this is not a linear equation in either x nor y. So it just either represents a true statement or a false statement, so it's not a graph of anything. And let's consider the more general case that a and b are not equal to 0, which is the general case of ax plus by is equal to c. So what I'm going to begin to do is I'm going to take this equation and I'm going to solve this for y. So I'm going to solve this equation for y, so I'm going to subtract ax from both sides of this equation. So I get the equation by is equal to negative ax plus c, and then I'm going to divide both sides of this equation by b. b is non-zero, so this is a fair move that I can make. So y is going to be equal to negative ax plus c all divided by b, which is the same thing as dividing each of the sum components by b, one of the basic properties of fractions. So we can rewrite this as negative a over b, x plus c divided by b. And this is going to be a very special relationship. So something that we need to figure out is, okay, what's so special about this number negative a over b, and what's so special about this number c over b? So consider 2 points. So consider 2 points, x1, y1, and x2, y2. And I'm going to take these and substitute them into this equation. So once I do that, I'm going to get two equations. I'm going to get y1 is equal to negative a over b, x1, plus c over b, and y2 is equal to negative a over b, x2, plus c over b. So this is an equation of a line, and I want the equation of the line that passes through these 2 points, p1 and p2. And if that is the case, then both of these equations must be true. So, what do I have? So the slope between these points p1 and p2, as we already know, is going to be y2 minus y1 divided by x2 minus x1. So this is y1, this is y2, this is x1, this is x2. So let's plug these equations into this relationship. So the slope between points P1 and P2 is going to be equal to y2, so negative a over b x2 plus c over b, minus y1, negative a over b x1 plus c over b, all over x2 minus x1. So I'm going to distribute this negative across that parenthesis. So I get that the slope between points P1 and P2 is equal to negative a over b x2 plus c over b plus a over b x1 minus c over b all over x2 minus x1. So as I see, c over b's will cancel, so we can just cancel them out. And I just have m of P1 and P2 is equal to negative a over b x2 plus a over b x1 all over x2 minus x1. So now what I'm going to do is I'm going to factor out a negative a over b out of the first term and the second term. So that's going to give us m of P1 times P2 is equal to negative a over b times x2 minus x1, all divided by x2 minus x1. Remember, x2 and x1 are just numbers, so these are just numbers that pretty much cancel out. So we're just left with negative a over b is the slope between these 2 points. And remember, these 2 points and this line are uniquely determined by the coefficients a, b, and c. So remember what my equation was. My equation was negative a over bx plus c over b, and I chose 2 arbitrary points on this line, and I noticed that regardless of those 2 points, that the slope between them only depends on a and b, which is the number in front of x. So the number in front of x, if you write it in y is equal to something x plus something, this number in front of x always corresponds to the slope, which most people abbreviate by m. So now we have y is equal to mx plus c over b. So what's so special about c over b? So remember, let's plug in 0 to sort of eliminate this term. So when x is equal to 0, y is equal to c over b. So what's so special about that? So if this is an equation of a line, when x is equal to 0, it corresponds to the vertical intercept. And typically, if this is the x-axis and this is the y-axis, some people just call this the y-intercept. So this number here corresponds to the vertical intercept. So therefore c over b is the vertical intercept, which some people just abbreviate as b. So therefore y equals mx plus b is a special type of the form of an equation, which is usually referred to as the slope-intercept form. Whereas ax plus by is equal to c is what we refer to as the standard form of the line. So solving for y from the standard form and putting it in the slope-intercept form can make obvious what the slope and vertical intercept of that line actually is. So let's work through an example to demonstrate. So example 1. So if I have 3x minus 2y is equal to 5, my goal is to find the slope and vertical intercept of this line. So I'm going to solve this equation for y. So I'm going to begin by subtracting 3x from both sides of this equation. So I get negative 2y is equal to negative 3x plus 5. And then I'm going to divide both sides of this equation by negative 2. So I get y is equal to 3 halves x minus 5 halves. So if that's the case, then my slope is going to be equal to 3 halves. So my line is going to be going up. And b, in this case, is going to be negative 5 halves. And this implies that my y-intercept is the point 0, comma, negative 5 halves. So, in summary, we have y is equal to mx plus b. M corresponds to the slope. B corresponds to the vertical intercept. Also notice that the entire right-hand side of this equation only has x in it. So that means this relation, r, is a function of x. And what do I mean by a function of x? That means it passes the vertical line test in terms of its graph. So if that is the case, then I can rewrite a line in the form f of x is equal to mx plus b. So this is what we call a linear function. So, as an example, consider the linear function f of x is equal to minus 5x plus 21. So, since this linear function is written by default in slope-intercept form, this number in front of x corresponds to my slope, and this number by itself corresponds to my vertical intercept. So if I want to graph this relation or function, so it's going to have a vertical intercept up here at 0, 21, and it's going to be decreasing since the slope is negative, so my line is going to be going down. So in terms of labeling the axes, this is my x-axis, this is my f of x-axis, and this curve in magenta is f, where my slope is equal to m, which is negative 5, and my vertical intercept is b, which in this case is 21, or the point 0, 21. And remember, saying the y-intercept is 21 actually has no meaning in this case because there is no y variable in this case. The vertical intercept corresponds to when x is equal to 0, the value of f is equal to something. There is no y to be considered here, which is why it's useful to talk about things in terms of its vertical and horizontal components. And if you talk about applications, some people call this the initial amount or initial condition, especially if 0 corresponds to time. And there's several applications that can be associated to this type of representation, but we'll discuss these applications at a later time. But this is just an introduction to linear functions. In the next video, we'll talk about a couple more properties associated to them.